Welcome back to the Deep Dive, the place where we sift through the sources, extract the golden insights, and get you up to speed on concepts that shape our universe.
And, more importantly, shape our understanding of it.
That's it, exactly. And today, our stack of sources is dealing with a concept that, well, it sits right at the intersection of science, philosophy, and just everyday observation. We're talking about emergence.
It's arguably one of the most intellectually compelling ideas out there, but it can also be a bit frustrating when you're trying to connect the dots between the very, very small and the very large.
That's our mission today, to dive deep into emergence. At its core, it's the idea that when parts interact in a wider whole, entirely new, complex properties or behaviors arise.
And these are properties that the parts just didn't possess on their own.
Right. We're not just looking at things that are complicated. We are hunting for that dividing line between systems that are merely complex and systems that are genuinely new.
And the framework for this is ancient, really. Aristotle put it beautifully. The totality is not, as it were, a mere heap, but the whole is something besides the parts. Emergence is just central to any theory of complex systems.
And what I love is how visual and just how everywhere this phenomenon is. Our sources give such powerful examples to ground the whole thing.
They really do.
I mean, if you just need a quick hook, think about the intricate six-fold fractal patterns you see in a single snowflake.
That's a perfect one. A single water molecule, H0, is a simple structure. But when millions of them interact under specific conditions, the right temperature and pressure,
you get this incredible self-similar complexity.
Exactly. That pattern isn't encoded in a single molecule. It emerges from their collective dance.
And it's the same principle in biology, just scaled way up. Take a termite. A single termite has, a few basic hardwired rules?
They're very simple rules. It moves, it finds food, it reacts to pheromones. That's about it.
Yeah. But when you get a whole colony together, this huge decentralized network of simple little bugs, you get these complex cathedral mounds.
These things regulate temperature, humidity, airflow. It's a sophisticated collective intelligence. But the blueprint for that cathedral is nowhere to be found in any single termite.
It's purely an emergent property of the group. And our sources say the ultimate example is life itself.
Right. Life, consciousness, self-replication. These are all seen as emergent properties of basic chemistry and physics.
You have hydrogen, carbon, oxygen, just atoms following standard laws.
But arrange them in a complex enough way, and suddenly you have a system that replicates, evolves, and eventually wonders about its own existence.
And it's just mind-blowing.
Philosophically, this focus on the origin of new properties is called emergentism. A thinker named Nikolai Hartmann even came up with a special term for them.
What was that?
He called them a categorial novum.
A new category.
A new category, exactly. It's not just an improvement on the lower level, it's a completely different kind of thing. The higher system depends on the lower parts, of course, but it operates with its own autonomous nature.
That really deepens the definition. We're talking about a change in what actually exists. And that brings us to the critical distinction we have to nail down because it's the fork in the road for this whole discussion.
It really is. This goes back to G.H. Lewis in 1875 when he coined the term emergent.
So he contrasted the emergent with the merely resultant. Let's start there. What's a resultant property?
Something that's resultant is just a simple sum or difference of its parts. The key here is that the components are homogeneous and commensurable.
Meaning you can measure them on the same scale.
Exactly. Think of two forces pushing a block. You have force A at 5 newtons, force B at 3 newtons. The result is 8 newtons of motion. It's traceable, predictable.
You can just do the math.
You can do the math. So if I mix 2 cups of blue paint and 2 cups of yellow, I get 4 cups of green. Predictable? That's resultant.
Okay, so what makes something emergent?
Well, this is the opposite. Lewis said emergence involved the cooperation of things of unlike kinds. The combination creates a property that is unlike its components because they are incommensurable.
Incommensurable. So they can't be measured or compared on the same scale.
Precisely. Take hydrogen and oxygen. You mix them, you get water. Now, try to find the property of wetness by measuring the properties of hydrogen gas and oxygen gas separately.
You can't.
You can't. Wetness is an emergent quality that operates on a totally different macro scale. It's incommensurable with the properties of its component gases. The whole introduces a genuinely new category of reality.
Okay, that sets the stage perfectly for the big debate. The difference between a really big calculation and something that genuinely introduces new rules. So let's unpack this core philosophical debate because that line is exactly what separates science from what critics might call, well, magic.
That's the perfect pivot, because the entire field is structured around this line. Philosophers like David Chalmers and Mark Bedell stress that you absolutely have to distinguish between weak emergence and strong emergence.
Why is that so important?
Chalmers says if you don't, it just causes enormous confusion, because they are, in his words, quite different concepts.
So let's start on the safer ground. Weak emergence. This is the one that's generally accepted in science, right?
Yes, complexity science, thermodynamics, physics, they all work with this. It describes new properties that arise from the fundamental interactions, but, this is the key, the property is still amenable to computer simulation.
So you can, in theory, model it.
You can model it. It might be what we call computationally irreducible, meaning even if you know all the rules for every component, you can't just write a simple equation to predict the outcome. The only way to know what happens is to run the full simulation step by step.
Like a traffic jam. I can't just write one formula for a traffic jam. I have to model thousands of individual cars making individual decisions over time to see where the jam forms.
Precisely. That's why traffic jams, or a flock of starlings, a murmuration, are classic examples. The system properties, like the swirling of the flock, are new. You don't see that in a single bird.
But the underlying rules are simple. Cohesion, separation, alignment. Just simple rules for how each bird reacts to its neighbors.
And Mark Bedell added that these properties are scale-dependent. You only see them if the system is big enough. The behavior might seem chaotic at the macro scale, but it's generated by microscopic parts that are fully deterministic.
So weak emergence is fascinating, but it's not metaphysically mysterious. If you had an infinitely powerful computer, you could trace every interaction back to the fundamental laws.
Exactly. It's a computational problem, not a metaphysical one. Which is why Bedell notes that if consciousness were just weakly emergent, it wouldn't really solve the classic philosophical questions. It would just mean the brain is a really, really complicated computer.
Okay, that leads us into the deep end. Strong emergence. This is where the friction is.
This is where the real debate lies. Strong emergence describes qualities that are utterly irreducible to the system's parts. The whole is truly, ontologically, other than the sum of its parts.
So if that's true, it means that new fundamental laws or new causal powers literally appear once a system hits a certain level of complexity.
And the consequence of that is profound. If a property is genuinely irreducible, then by definition, no simulation of the system can exist.
Why not?
Because if you could simulate it, that simulation would be a reduction of the system to its components. It would immediately collapse it back into weak emergence. Strong emergence says there's a genuine novelty barrier you can't cross with a computer.
Now, this is where I have to push back a bit. If you're saying this new property can't be reduced, can't be simulated, doesn't that make it scientifically untestable? Where does this new thing come from ex nihilo out of nothing?
And that is the core challenge. As our sources state, strong emergence is rare, if not entirely absent, in well-established physics. Bedell famously said that while it's logically possible, it's uncomfortably like magic.
The dreaded magic critique.
Yes, because it suggests you're illegitimately getting something from nothing. It seems to violate a fundamental principle. Ex nihilo nihil fit nothing comes from nothing. If the parts don't contain the potential for this new power, where does it come from?
It sounds like a philosophical dead end. But then we get to the idea of causal overdetermination from the philosopher Jaegwon Kim. This seems like a direct logical attack on the idea.
It's the primary hurdle for strong emergentists. Kim's argument is all about downward causation.
So the idea that the emergent property at the high level can cause an effect at a lower level.
Exactly. So let's walk through it. Say you have an emergent property, M, like our wetness example. And M depends entirely on a physical base state. P, the arrangement of water molecules.
Okay, so M is the emergent property, P is the physical base.
Now let's say the wetness, M, causes a paper towel to absorb water. That's a new state, M star. But that absorption also have to have a physical basis, P star, right? The actual capillary action in the paper fibers.
Okay, so M causes M star, and P causes P star.
But here's the problem. We already know from physics and chemistry that the physical state P, the water molecules, is sufficient on its own to cause P star, the absorption.
The laws of physics say P causes P star.
Right. So now we have two causes for P star. We have the physical base P and we have the emergent property M.
It's being caused twice.
It's being caused twice. That's the overdetermination problem. If the physical base P is already doing all the work, then what is M for? It's redundant.
And Kim argues that's highly implausible.
It's more than implausible. It's a killing blow to their idea. The whole point of strong emergence is that the new property should make distinctive and novel causal contributions. But if the underlying physics is already doing everything, then M is causally irrelevant. It's just a label we put on a complex physical state.
So this argument really foices us back into the domain of weak emergence, where everything is, in principle, reducible.
It definitely explains why strong emergence is treated with such skepticism. It seems to require a violation of what's called causal closure, the idea that every physical effect has a sufficient physical cause.
But even if that's the philosophical limit, the sheer practical limits of reductionism in science are still profound. I mean, scientists can't actually sit down and calculate everything from first principles.
Not even close. And that takes us right into how the hard sciences, especially physics, actually deal with this challenge of scale and complexity.
Right. So in physics, we're mostly dealing with what philosophers call weak emergence.
We are, but physics frames it in terms of necessary descriptions. We're talking about properties or laws that only occur at macroscopic scales, vast scales in space or time, but not at microscopic ones.
Nobel laureate Robert Laughlin had a lot to say about this. He said, for any system with many particles, you just can't calculate everything exactly from the microscopic equations. It's too complex.
And even more importantly, he highlighted the role of broken symmetry. The fundamental equations for the microscopic particles might be perfectly symmetrical, but after a phase transition like a liquid freezing into a solid, that symmetry is gone at the macro level.
So the laws governing the microstate don't look like the laws governing the macrostate. If I look at a block of ice, the underlying HO molecule equations are symmetrical, but the actual crystal lattice of the ice is not.
Precisely. And so, Laughlin argues, macroscopic systems have to be described in their own unique terminology. They have properties that don't depend on many of the tiny microscopic details.
Yeah.
You use fluid dynamics to calculate airflow over a wing. You don't track every single air molecule.
This sounds exactly like the argument from Philip W. Anderson's famous 1972 essay, More is Different. That was a landmark piece of writing.
It really was. Anderson directly attacked what he called the constructionist hypothesis, that reductionist dream, that you could start from fundamental laws and just build the entire universe up layer by layer.
And he said that idea just breaks down when confronted with the twin difficulties of scale and complexity.
Yes. And that led to his powerful defining quote, "At each level of complexity, entirely new properties appear. Psychology is not applied biology, nor is biology applied chemistry."
He essentially gave scientists permission to study their own fields as fundamentally independent, even if we know everything is ultimately based on physics.
It forced scientists to be emergentists in practice, even if they're reductionists in theory. And it turns out the complexity doesn't just make calculation hard. Sometimes it might make it impossible.
This is that finding about the non-computable universe from Gu and his colleagues. Non-computable, how can a physical system be literally impossible to calculate?
Well, they showed that for certain infinite physical systems, if you could systematically calculate their macroscopic properties from the microscopic description alone, you'd also be able to solve known undecidable problems in computer science, like the halting problem.
Wait, so the universe's complexity is linked to the fundamental limits of logic itself?
It seems so. It creates a kind of protective shell around the macroscopic world. It implies that a theory of everything that describes all the fundamental particles is necessary, but it might not be sufficient for a complete understanding of the universe.
So those macroscopic laws, like thermodynamics, might still require conjectures suggested by experiments, simulations, or insight. We have to look up the hierarchy, not just down.
Which is why this is such a vital area of research. And some recent theoretical work is actually trying to find mechanisms for strong emergence, for true novelty, right at the quantum to classical transition.
This brings us to that really cutting-edge stuff from 2025 in our sources. Let's look at Gerge's theory of emergent motion, or TOEM.
Right. So we usually assume that the classical motion we see every day, a ball rolling, is just an inherited property from quantum mechanics. TOEM challenges that.
How so?
It proposes that directional motion actually emerges as a probabilistic resolution only after a tiny discrete time threshold, what they call $t$. Before that threshold, there's quantum uncertainty. After it, a deterministic trajectory snaps into place.
So motion isn't a constant, it's a phase change. It freezes into reality.
Like water freezing into ice, yes. It's an attempt to put a rigorous mathematical framework around an emergent event, suggesting motion itself is a fundamentally emergent property.
And what about the emergence of space-time itself? That's Prakash's vibrational dynamics framework.
That one's even more mind-bending. It suggests that gravity space-time curvature emerges from complex, standing wave patterns in vibrational fields.
So the grand structure of the universe emerges from tiny quantum jitters stabilizing into a fixed pattern.
Exactly. The novelty there is defining the mechanism by which random quantum noise can stabilize into the fixed geometry of classical gravity. And later work even suggests that entropic mechanisms, disorder, and friction might actually drive that process, pushing the system past that $T threshold.
So noise and complexity aren't just a problem to be solved. They might be a constructive, necessary force.
That's the idea.
That gives us a remarkable perspective on the inorganic world. But what happens when we go even further up the complexity ladder and introduce, well, us, consciousness, free will, human interaction?
Right, moving from inanimate matter to sociology. Now, the components, human beings, are already immensely complex, yet their interactions create massive structures that none of them individually intended.
This is the idea of spontaneous order in society. Our sources point to Max Weber's classic, the Protestant ethic, and the spirit of capitalism.
A perfect early example. Weber argued that the system of capitalism emerged, in part, from the collective actions and beliefs of individuals who were just focused on their own salvation. They weren't setting out to invent the global economy.
It just emerged from their interactions.
It did. And you see this aggressively in emergent economics. Under capitalism, growth and innovation are emergent. The system becomes a self-expanding spiral.
And that's driven by a positive feedback loop, isn't it?
Yes. New tech increases productivity, which leads to more capital, which funds more research, which leads to new tech. The engine of modern economics is an emergent phenomenon fueled by its own output.
Karl Polanyi wrote about how this emergent process completely transformed society when things like labor and nature were turned into commodities.
That shift set the stage for our entire industrial society. It wasn't planned. It emerged from the interaction of these new market rules.
And this brings us to the really fascinating area of how we can tend to emergence in human systems. Peter Senge's work comes to mind.
Senge argues that living systems, families, organizations, economies are continuously creating themselves. And if we try to manage them with a machine-age mindset of control and predictability, we'll just keep recreating the same old institutions.
Which leads right to the work of Nora Bateson and the International Bateson Institute. They don't try to predict what will emerge. They ask a different question.
A much better question. What makes a living system ready to change?
They call their approach readying. Instead of a 5-year plan with a fixed goal, you focus on tending the prelude to change. You nourish the system's flexibility, even if you don't know what crisis that flexibility will be needed for.
And their practical method for this is the Warm Data Lab. They bring together people from completely different backgrounds, a city planner, a biologist, a farmer, to talk about the same complex issue from their own unique contexts.
The goal isn't to find consensus, but to allow for something new to unfold. They call it aphenopoetic phenomena. That's a mouthful. What does it mean?
It literally means unseen creation. It's the inherent flexibility or capacity for a novel response that is unseen and unknown within the system. It's the potential for the system to adapt in a way no single expert could have predicted.
Okay, can you give me a practical example of that?
Imagine a city facing crises in housing, water, and transit all at once. A traditional approach tackles each one separately. A Warm Data Lab gets everyone talking about all three together.
And what might emerge?
The group might realize that a decentralized, community-managed water recycling system, which solves the water problem, could also double as a neighborhood meeting place, solving social isolation and reducing transit dependence.
So a single novel solution to 3 problems that wasn't on anyone's radar.
Exactly.
Yeah.
That's the aphenopoetic potential. You don't plan it, you cultivate the conditions for it to emerge.
It's a profound shift. And we even see this in something as basic as how we communicate every day. Linguistics has the concept of emergent grammar.
The perfect example of spontaneous order. Grammar isn't a set of top-down rules. It emerges from millions of speakers just trying to solve communication problems efficiently.
So no one decided we should all start using latus as a discourse marker. It just happened.
It just happened. If enough speakers find a strategy works, it spreads and eventually stabilizes into a new grammatical convention. The rules of language emerge purely from the microactions of its users.
So we've seen emergence in physics, in society. Now let's bring it right down to daily life and address one more philosophical twist. The role of the observer.
Yes. James P. Crutchfield made the point that complexity and organization are sometimes subjective qualities determined by the observer. Emergence isn't always an objective fact about the world. Sometimes it's about our perspective.
How does that work?
Think about a perfect diamond. An observer sees a beautiful, ordered, low-entropy structure. We call that order an emergent quality.
But we only see that order because we're deliberately ignoring the chaos underneath. The vibrating molecules, the quantum foam, we're sort of squinting.
That's a perfect way to put it. The order is, in that sense, subjective emergence. We've chosen a simpler macroscopic model that ignores the microscopic noise because it's computationally easier for our brains.
And the same goes for something we call chaotic, like the weather. We call it that because we can't process the position of every single air molecule, even though we assume it follows deterministic laws.
Exactly. So what we define as emergent can be a reflection of our own computational limits.
Let's make that even more tangible. What about emergent artifacts, human inventions?
Artifacts are created for a purpose, which makes their emergence subjective. Take a hammer.
A metal head and a wooden handle.
Individually, they have properties, but connect them in a clever way and you get the new emergent functionality of driving nails. And that function allows for downward causation.
Meaning the purpose loops back and changes the components?
Exactly. The desire to drive nails more efficiently leads us to optimize the head's weight or the handle's grip. The emergent property driving nails causes improvements in the underlying parts.
You see the same thing with bronze, right? A mix of tin and copper.
Which has new emergent properties.
Yeah.
It's harder and, crucially, has a lower melting point than either metal alone. That allowed early metallurgists to cast complex shapes. The desire for that emergent property drove the entire process.
We even see emergence in our technology, like with internet traffic.
Oh, absolutely. Congestion is an emergent property of the network, and sometimes that congestion can cause all the TCP flows to globally synchronize. They all slow down and speed up together like a giant coordinated pulse.
A behavior no single part was programmed to do.
And we even simulate emergence in AI. The boys program simulates a flock of birds. Each boy just follows 3 simple rules, but the collective flocking behavior is incredibly realistic.
And in all of these cases, artifacts, living things, the concept of supervenience is key.
Right. The emergent whole always supervenes on its crucial components. A construction error, a software bug, a genetic mutation. The emergent result is always tied to and dependent on its physical base.
Which reminds us that the line between just complex and truly new is a moving target, depending on the system and on the observer.
We have covered a huge amount of ground today. We started with that philosophical challenge from G.H. Lewis. How do you distinguish something truly new from something that's just a sum of its parts?
And we wrestled with Jaegwon Kim's logical crisis for strong emergence, the problem of causal overdetermination. If the physics is already doing all the work, what's the emergent property for?
And yet we saw how science, following Philip Anderson, has to accept the practical limits of reductionism. At great scales, new laws are required, and some things might even be fundamentally non-computable.
We then charted emergence as a driver of human systems, from the spiral of capitalism to the spontaneous order of language, and that incredible work being done to simply ready our systems for an unpredictable future.
The lesson is clear. Reductionism has its limits. The universe is a hierarchy, with novelty constantly bubbling up. There will always be levels of reality that require new laws and new insights.
The world is, in a very real way, continuously creating itself.
Which brings us to our final provocative thought for you. If we accept that weak emergence means a system is still, at bottom, just a giant calculation, but strong emergence implies true, irreducible novelty that changes the rules.
Then where do you draw the line? Think about the human mind. Is consciousness just a tremendously complicated traffic jam of neurons, a weakly emergent property of a complex but ultimately reducible machine?
Or is the mind a true categorical novum, a property that transcends the physical laws of the brain and possesses its own novel causal powers? We challenge you to apply these ideas to your own life and work. What do you believe is merely complex, and what do you believe is truly emergent?
Thank you for joining us for this deep dive into the unpredictable logic of emergence.